In this video, we'll briefly go through the steps that will be required in the analysis of your engine for the project. As you work your way through the project, you may find it useful to come back to this video when you come to analyse some of your engine's components. You've been given your engine's flight Mach number and the static pressure and static temperature of the air at the altitude your engine is flying at. These are state 1. The first step in the analysis is to calculate some further properties of the flight condition. You'll need to work out your flight speed V1 and the density of the air through which you are flying, ρ1. You also have to determine the conditions you would obtain if you brought this flow to rest isentropically. That is, the stagnation conditions of the gas. To find these, you'll use things like the equation of state and the isentropic flow relations. So refer back to sections 1 and 2 of the course. Then you start working your way through the engine, calculating the flow conditions at each step. First, you calculate how the flow conditions change across the first shock in the inlet, shock wave S1. You have to calculate the conditions of the flow at state 2. So, you know all of the conditions at state 1, and you know that the flow is deflected through an angle θ1. You can use your oblique shock wave analysis to find your shock wave angle β1 and the pressure, temperature and Mach number at state 2. Then you move on to the second shock wave in the inlet, shock S2. Refer back to our example of the 3-shock inlet from section 3 of the course. You know the flow is deflected through an additional deflection angle of θ2 to take the flow to state 3. So, oblique shock wave analysis will again give you the shock wave angle, β2, and the flow condition at state 3. The next step is to move on to the third shock wave in the inlet, shock S3, so that you can calculate the conditions at state 4. Again, it's oblique shock wave analysis that you will need to use. It's important to note that the last shock turns the flow back through an angle of θ1 plus θ2 so that it's parallel to the surfaces of the combustor and to the direction of the oncoming flow. So the shock angle β3 is the angle the shock makes relative to the oncoming flow, the flow at state 3. You're now ready to analyse the flow through the combustor. But before you do that, I want you to calculate the overall drag force on your inlet's aerodynamic drag. This is where one of the important assumptions we are making comes in. Remember that we are neglecting any forces due to viscous or skin friction drag in the analysis. So the only aerodynamic drag forces on the inlet will be the forces due to the pressures acting on the inlet surfaces. Let's look at the first inclined surface of the inlet. Pressure P2 will act on this surface. P2 will act over the area of this surface of the inlet, its length times its width, to produce a resultant force F1. Now, if we're interested in the aerodynamic drag force, we're only interested in the component of this force that's acting in the direction of the oncoming flow. So that is the aerodynamic drag force acting on this surface of the inlet, and we can call that D1. By the same reasoning, there will be some drag force due to the pressure P3 acting on the second inclined surface of the inlet. This will act over the area of that surface to produce resultant force F2. And the component of this force contributing to drag we can call D2. There are no other forces on the internal flow path of the inlet that can produce any force in the direction of the oncoming flow. So the total aerodynamic drag on the inlet is just D1 plus D2. Right, so now we are ready to move back on to look at the combustor. Let's zoom in on it. The combustor will take the air from state 4, the condition we've calculated at the end of the inlet, to state 5 at the end of the combustor. Along the way, you will model the heat release Q using the Rayleigh flow analysis you learned in section 4 of the course. So you'll have to do some analysis to determine from your equivalence ratio just how much heat your combustion will release. And then you'll use that to find the conditions of the air at state 5. A couple of points here. Because you are not including any viscous effects, you can ignore the effects of viscous friction in the combustor. So you don't have to do any Fano flow analysis or viscous skin friction calculation for the project. That reduces the complexity of your analysis, but you'll need to remember that this is a significant assumption. So you should get better performance out of your engine than you would if you included viscous effects. The other point I wanted to make is that this assumption means that there is no aerodynamic drag or thrust force acting on the combustor. Because the combustor is aligned with the flight direction, the pressure forces in the combustor only act normal to the flight direction, and therefore these pressures don't contribute to the drag. So there's no aerodynamic drag for this combustor with the present modelling. The next step is the nozzle. The nozzle expands the flow from state 5 to state 6. Since you know the heights at the entrance to the nozzle, H3, and at exit from the nozzle, HE, you can use the isentropic flow relations to work out the conditions of the flow at state 6. Then you'll be ready to calculate how much thrust your nozzle produces. To calculate this, you'll need to put a control volume around the nozzle and look at conservation of momentum in the direction of the flow. We'll call it the x direction. You'll need to consider the forces acting on the control volume. There will be the pressure forces at entry to the control volume at state 5 due to P5 acting over the area there. There will also be pressure forces at exit of the control volume at state 6, due to P6 acting over the area there. And there will be the force acting on the control volume in the x direction. Let's call that T. Another important point here. T is the force acting on the control volume. An equal and opposite force acts on the scramjet nozzle, and that force is the thrust force on the nozzle. You'll have to do some careful thinking and modelling here and balance the forces acting on the control volume with the change in momentum flux of the air passing through the control surfaces. Finally, you can put it all together. The net thrust of your vehicle will be your nozzle thrust minus the inlet drag, which will hopefully be greater than 0. Then you can find your engine's specific impulse ISP and your point on the ISP versus Mach number plot for the class. So that's enough from me. It's now over to you. Good luck with the project. I hope you found the course interesting and informative, and I wish you all the best in your future endeavours.